Good afternoon, everyone. Thank you for coming. Today we have Michael Gartner from Photon Energy, so it's great to have him. Michael did his, Michael or Mike?
Michael.
Mike. So Mike did his economic degree in Manchester, Newcastle University. And then he did his MBA in Rochester in New York. He started his career as a investment banker in Prague, from all the places. And then he co-founder of Photon Energy and moved to Australia to direct the office here. I will not speak too much on Photon Energy because Mike will introduce that. So let's start, and please welcome Mike.
Thank you, Zev. And thank you, everybody, for coming today to the presentation, which I hope you'll find interesting and coming more from the commercial side of the business, where the technologies developed at institutions such as UNSW get utilised and become part of all the incredible things that are happening out there with the development of a new energy sector. What I would like to do today is actually speak to you a bit about what we do, because as an integrator, it's very much about how we control and utilise the energy coming out of solar panels or wind generators and so on and so forth. And that's why I've called the presentation Controlling and Storing Solar Power, an Integrator's Approach. Now, what I'd like to say about that first is that actually the energy that we're using right now, powering these lights and screens and so on, it was only generated a few moments ago. And if a power plant would stop working, another power plant would basically have to make up for it. However, our current energy system is not really capable of reacting so flexibly to changes in demands. So our coal and, not in Australia but elsewhere, nuclear power plants are just left running, which wastes enormous amounts of energy. And also we have enormous solar and wind energy resources that we can utilise, but the problem with those is that they can't adequately be utilised because they're not necessarily needed when the power is produced. For example, the solar panels we have on our households, generally people are not at home during the day when the power is produced, so it has to go back into the network. And this is basically why we really need energy storage. There's different types of energy storage, such as pumped hydro, which is a very mature technology. But increasingly, we're finding that different types of chemical storage in batteries or other means, mechanical means, such as flywheels and so on, are coming more and more into play. For off-grid locations, and in many cases even behind the meter, the storage in chemical batteries is actually becoming one of the most effective solutions we have. And we know that from the analogy of mobile phones, for example. These are all devices which have a battery inside them. We recharge them at night and use them during the day. Chemical batteries are also the fastest developing area of energy storage. We have technologies such as lithium-ion technologies, which basically branch out into four main areas, including the highly publicised NCA technology, which is utilised by Tesla, for example. And we always like to thank Elon Musk for putting so much into PR of battery technology and storage technologies through their automobiles and so on. But we shouldn't forget that there are other technologies out there, such as nickel cadmium, nickel metal hydride, zinc bromide, and we should never forget actually the good old lead acid batteries that are still the most widely used form of battery storage. And in that area there is some massive progress being made as well. For example, you've got the valve regulated lead acid today, and you also have batteries incorporating supercapacitors, for example, to improve their capabilities. And some of those technologies actually being developed in Australia and commercialised in Australia at the moment. It's not without a challenge. Most battery systems we have today are very small, being really utilised for specific tasks such as powering telecommunication antennas and so on, or small repeater stations. And when you get moving into the large-scale storage, the big challenge becomes how to manage those systems to keep them safe and stable in grid environments or in major commercial applications. And that's increasingly become a challenge. So that's basically where our company kind of comes into play, because we're a dedicated team of engineers and programmers who understand electricity and the role and importance of regulation, protection and control. And we've basically spent many years developing and perfecting our own monitoring control systems that enable us to do great things with power components, which we tend to refer to as toys, usually, because there's so many of those components that we usually have to integrate and put together. And these include, of course, the batteries, the sensors, the chargers, inverters, PLCs, and other interesting circuits that we develop and use. And we also call that process herding cats, because each of those technologies that we get ends up being something which is provided by a certain manufacturer with a certain type of software driving that device. And very often the big challenge we have is to actually combine all those different control mechanisms together to make them work as one. And that's basically why we've developed our internal SCADA system. In Australia, we have one of our first integrated devices that actually runs on our command and control system. And that's something I would like to present to you today, amongst other things. So if we go on to some background about Photon Energy, we're a company which is relatively young. We set ourselves up in 2008, actually set ourselves up in Prague, because at the time it was one of the first adopters of a feed-in tariff mechanism in Europe. So after Germany and Spain, it was actually the Czech Republic who came out with a feed-in tariff mechanism. And we saw a great opportunity to build a company, build an integrated business model. And we started developing and implementing projects. Over time, we've become a system solution provider, and we have really concentrated our efforts in the engineering and programming side of things, and also the long-term operation and maintenance of systems. So we've set up control rooms, and we've set up control mechanisms to enable us to effectively manage assets without having to go out to fix every single little thing that happens at those sites, and with a hands-on approach, which is quite often the approach that is still used today. We have over 170 megawatts of assets that we operate. We've actually built about 80 megawatts of assets ourselves, and we own and operate about 25 megawatts of solar infrastructure in Europe, which is mostly grid connected. Interesting thing is that we're expanding in Europe, mainly in the operation and maintenance space today. But Australia being basically my home market, because I'm one of the founders of the company, but grew up in Australia. It was kind of a natural move for me to come down here. It was always on my mind, why do solar or renewable energy in Europe when Australia has some of the best renewable energy potential in the world? So when I came back a few years ago, my whole idea was to really push our business model forward. Okay, now I'd like to tell you a little bit more about some of the work that we've been doing in Australia. What we have, one of the projects that we recently commissioned, that means we completed this project in November last year, and it was a project that we were commissioned to do by Broadcast Australia, who runs a significant, most of the broadcasting that is done in Australia actually runs through Broadcast Australia infrastructure. It includes television, radio, and essential services. They are very keen to transfer as many of their sites as possible to an autonomous energy system for multiple reasons. One of them is, of course, to utilise renewable energy. Another one is strategic concerns about energy supply to the locations where they have antenna infrastructure, and of course they have very strict uptime requirements which are laid down upon them by all of their customers, including the ABC, for example. You wouldn't want the television signal, or sometimes you might not mind if it drops out, but they do have the uptime guarantees that they need to provide to those services, and also to the army and to the police, for example. And also, if you imagine a case of state of emergency, very often radio is still the only way to get information to people who are affected by bushfires, floods, and so on and so forth. So those concerns are high on the agenda. And ultimately, you also have the question of costs, variability of costs of power supplies and of diesel, which is often used as a backup generation medium at most of these locations. So what came out of that discussion with BAI was actually a pilot project. Now, what we did first to look at the site was to actually get the facts straight. So, as an integrator, you really have to start from the ground up. And most of what we did in order to understand the energy situation at that site was to look at the energy demand data of all the equipment that is used at that site. Now, it's an AM antenna. It has multiple channels which it's broadcasting. So for each of those, it has equipment which would be provided to that site by the broadcaster. So you can imagine you have a rack of equipment there running at different frequencies to provide different radio signals from, let's say, from ABC National or the local commercial radio stations. And that infrastructure uses a certain amount of power. So it's quite constant because radio signals are transmitted 24/7. So that's one of the aspects that had to be considered. But it also needs to be kept cool in summer, sometimes even kept warm in winter. So there's additional power demands which fluctuate. So we had to take all these things into consideration. And based on that, we build an energy model. So we actually use some systems that you may be aware of. There's a system called Homer, which we use extensively in our energy modelling, which is a fantastic system. And that enables us to then create a return analysis. We also looked at life cycle costs, so what it costs to actually operate that infrastructure, how many times you'd expect to have to go out there to do maintenance, how often there might be a problem with the system and the need for a technical intervention, but also how to ensure that that system is kept healthy over the long period of time to ensure that you don't excessively increase those costs. And of course, then you have to think about how to implement it. And the interesting thing about infrastructure like this is that very often it's very remote. So to actually get there can be very difficult. And usually you want to implement as much as possible off-site. So when you get there, it's really just about installing the equipment and not about commissioning and ensuring that the systems are functional. So basically, what did we come up with? After we've done this analysis, we came up with a system that should provide as much as possible autonomy to the broadcast antenna. Now, autonomy is an interesting concept because generally what you'd be trying to do is get, let's say, 100% of your energy from renewables. But very often that's not practicable because you have to actually increase the storage capacity pretty much on an exponential basis. So what we do is look at it from a perspective of, let's say, achieving an optimal cost level. When we ran these algorithms, we realised that for this site to have about, it's actually over 90%, it's about a 94% autonomy. We needed to have about 216 kilowatt hours of battery storage, which was charged by 39 kilowatts of solar, and it's running a load which is somewhere in the vicinity of about 6 to 7 kilowatts of constant load with slight variability. Now, what happens in the situation when we don't have enough solar potential, and we do have weather events? We've been monitoring the system now for about the last 6 months, and we've realised that when we do have long weather events, the backup generation simply has to kick in. So there's two reasons why you have the backup generation there. One of them is to maintain the redundancy in the system because you have to provide power, but also you want to protect the batteries. So you're looking at a depth of discharge at around 30% level of charge in the batteries, where the generator will kick in to preserve the life of the batteries. And that's basically the system. So it's relatively, there's a good, strong theoretical and practical basis as to how you would dimension a system like this. We've used lead-acid batteries for this system, and there were some considerations that we made as to why we chose that technology, because we did look at lithium-based technologies as well. Now, the considerations were that we had to have a technology which was actually highly available, and also highly available in Australia. So we selected a manufacturer with a very strong distribution base in Australia. The reason is that if you do need to replace things, you want to have supply available at any point in time. And also, when we looked at the type of load that has been used at that site, as I said, it's a relatively constant load. Now, for that sort of load, a lead-acid batteries actually seem to be quite good. They have relatively flexible charge and discharge rates, which is very important because when we're storing energy from solar, we generally have a lot of power available during the midday, and so our charge rate is very quick, whereas the discharge rate is quite slow. So this additional flexibility is quite useful in VRLA. They can, carry an incredible amount of current. It's actually amazing what they can do. So for that sort of perspective, it was a very good choice. We also have a deep cycling ability of this particular technology because it is VRLA, and it's a proven technology with long life. The batteries we used actually come from Germany. It's a manufacturer called BAE Batterien, and they've been making batteries actually all the way back to World War II. Some of their batteries are still functional today that were made back then. And they are and continue to be an important supplier for the defence industry. They provide batteries for submarines. And their batteries actually went into German U-boats, which I'm not sure is such a good reference, but certainly they've got proven reliability. And then it's about the low cost. They're still a very low cost. They're still lower cost, even though Elon Musk has made a very good effort at pushing costs down. Lead-acid continue to be the lowest cost alternative on a levelised cost of energy basis. So what I've basically said most of this already, but that's just looking at this graph here will show you what the planned autonomy of the system is. So the big long orange line, that is the amount of power that we're supplying from the battery storage system, and the red area is the amount of power we're providing from the diesel backup generation. And as you can see, that diesel backup generation is mostly required in the winter months when the solar potential is reduced. And at the bottom here, you can see the state of charge of the battery bank, and there you can see as well that in the summer months we have generally a complete full charge cycle, whereas in the winter months we're not quite getting there with charging the batteries, and that's of course simply due to the climatic factors. The interesting thing is that so far the system, it's only been operating for the last 7 months or so, but during that period the uptime performance has been 100%, which which is very good, and it's something very, very encouraging about these systems. They are actually highly reliable, and that's a very important thing to say and add to the discussion. Now, this is just to show you how that sort of charging and discharging cycle is working there. What's happening is basically, now that blue line, the dark blue line, is basically showing you what's happening on the charging end of things. You can see that the amount of charge current that we're putting into the batteries is about 7 times the output current. So we're charging the batteries quite fast. That's the nature of solar power. It's got a lot of power middle of the day and basically reducing curve in the afternoon and increasing curve in the morning. So what happens is that we charge the batteries very fast. We get to a point at about 2 p.m. in the afternoon, I think in summer, where the batteries are fully charged. They go into float cycle, and the excess power from the solar system is then no longer used, or it just goes through the whole circuit. It's a DC coupled circuit, so it's basically passing through the inverters straight into the power consumption. And then we can see that as we go throughout the day, we're getting to a point where the batteries are starting to discharge, and you can see the state of charge there. The reason I've chosen this particular graph is there's an interesting thing there. There's one day which was overcast. So you can see that the second day, we haven't managed to get to a full state of charge. And some of the charge from the previous day has been carried over into the next day. And the system is basically designed to easily cover 2 days, sometimes 3 days of autonomy, but already on the fourth day, it really doesn't make sense to cover that from storage. We'd have to basically be increasing the storage capacity significantly to cover ourselves for a fourth day. So it's not cost effective. And the other interesting thing about this is if you look at the temperature of the batteries, you can see that temperature spike goes up while we're charging the batteries, not discharging, because of that speed of charge. So it tells us something about how that system needs to be controlled, and also gave us some interesting information about cooling, because we do have a cooling ability there. But one of the interesting things that we've done is we're tweaking the cooling so that it's only cooling during that charge period, so that we keep the battery temperature down, because we don't really need to the rest of the time. Here I'd just like to say something about the drivers of the cost of systems. So as I said, every single site or every single use of battery storage can be quite different, and the different functionality that you would expect from battery systems, such as peak shaving, load shifting, autonomous supply, and so on, they all have different types of energy utilization, and that will, of course, dictate the capacity of the system. It will dictate the output, so how many kilowatts of power you actually have to deliver from that system to your energy consumption. The purpose of that system, where it's located, as I've said before, and also the operation and maintenance of that system. So these are the critical factors that will impact price. So when I see sort of like generalizations such as the cost per kilowatt hour or cost per kilowatt of output and so on, it doesn't really make much sense, because if you have a system where you need to cover a very high load, so you may have 200 kilowatt hours of battery storage and 100 kilowatt of throughput, because you only need bursts of power. Now, if you could run that system, for example, as it is set up in Muswellbrook, you're only putting out about 7 kilowatts of power. So that system is going to have a different dynamic and a completely different sort of pricing to a system with a high output, for example. And of course, a different battery chemistry is probably useful for that sort of purpose. So the high throughput will require probably a battery with much more cycling ability, such as lithium-ion. Now we have some value drivers as well. So when we're looking at what is the cost of supplying the energy, we also have to balance that out against what is the actual benefit that we provide the customer from that. And that will also depend what your alternative generator is. An alternative generator can be the grid. It can be existing infrastructure available on site. And of course, it has a certain price. It also depends on the service provided, as we've mentioned. It depends also on the time of use of that power, because power can have a different value at different times of the day, as we know from the national energy market. And whether or not it's behind the meter or into the grid. And there's an interesting situation now, a huge discussion globally, but I think California is the first place in the world to actually implement this. Battery storage is now being considered as a service to the grid, so they do not pay the grid charges at all, which is a very good thing, because they are storing energy when it's abundant, and they are giving energy back when it's needed. So it's certainly a big factor in the value driving, and it's a discussion that we certainly need to have in Australia to encourage more power storage to be deployed, particularly in the grid environment. And then finally, you also have the system control. So how you actually approach how you utilise that energy to maximise its value. So a simple analogy of that would be, if power is cheap from the grid, I store it into the battery. If it's expensive in the grid, I should be discharging my battery to the grid, for example. So it's that sort of control in the background which will also add value to battery storage. This graph here is actually showing from the perspective of our Muswellbrook project, so it could look a bit different for other projects. But what we did was we also looked at the cost of, it's basically an iterative process looking at different combinations of solar energy or solar system and battery system. So you'd be looking at how much of that load for that customer, given their load profile, you could actually cover from your that combination of solar and storage. And basically what happens is at that lower end of the curve, where you can see the levelised cost is about 12 cents or so per kilowatt hour. That's basically the current cost today over a 20-year period of solar PV. Now, you can cover about 20% of the energy requirement of that site simply by having solar and no battery, because all that power can be utilised at the time of production. Now, as you try and increase your autonomy, of course, you have to add more storage and more solar. So your solar is increasing because you have to store more energy, and your energy storage increases so you can cover more energy. So this iterative process, and we increase costs gradually as the system size increases. And you can see from that graph that where we have created a cutoff point was basically at a levelised cost of energy of about 40 cents per kilowatt hour. And we decided that it didn't make any sense to go any higher, because the alternative cost of energy on that site, which is a diesel generator, would probably be able to cover that energy at a similar cost. And then when you're going into the level of autonomy, so the percentage at the bottom, which is higher and higher, that cost is actually increasing, starting to increase exponentially. So there seems to be a kind of a sweet spot that you can find for just about any configuration of system that you would be implementing. And it's definitely important to look at that and to understand what the value of the energy is being provided and compare that to its cost. There's another factor here which I mentioned before, which is basically herding cats. The reason we call it that is because cats generally don't like to be herded. I don't know if anyone has a cat who understands what they're like, but generally when you look at system control, you do have a lot of cats to control, and they don't like to communicate with each other necessarily. So part of the challenge of the integration is to actually make inverters talk to chargers, and make battery management systems talk to chargers and talk to inverters, and so on and so forth. Also, backup generation is part of the picture. When it kicks in, how does that kick in? What is the frequency when it kicks in? And so on and so forth. And this is a real challenge. It's a real challenge that we discovered several years ago when we started looking at integrated systems, and realised that in order to do it properly, you really had to attack the control side of things. So looking at it from a data acquisition and control perspective. And of course, what that also leads to is how you can do your remote control and your remote monitoring, because it's a critical part of the whole picture. The more you can do off-site, the better, because costs of sending technicians to site is generally quite prohibitive, very high, and makes power storage unattractive, actually, in many respects. So we try and keep that to a level where it's down to the bare minimum. There's also increasingly what's important to become demand control, and that's very interesting because that can change also the cost perspective greatly by turning down non-essential services when there's not enough energy available and so on. I think it's important also to add always the safety and compliance aspects as well. You want these systems to be safe. You don't want them to end up in a catastrophic situation. For example, some battery systems have burnt in real life situations, and this is something we have to avoid and prepare for. And of course, the compliance issue is becoming much more important as the technologies develop. The regulations are catching up. And it tends to be always the case. The regulations catch up, and sometimes they throw interesting problems back at you that you need to solve as a system integrator. So the compliance issues become very important. So what is it about an integrated SCADA solution that's important? It's the communication and monitoring, which enables you to extract data and analyse data, and also look at the system health and ensure that the system is functioning correctly. There's an increasing interest also in this adaptive algorithmic self-control, so looking at system health and understanding what that means from a perspective of optimising the SCADA controls, and it's quite a new area with a lot of potential in reducing balance of system costs, in particular for storage systems, very important. You also have the remote control aspect when you do need to turn things on and off or ramp things up and down for whatever reason. You need to be able to do that remotely without necessarily sending a technician to site. Then you've got signals and alarms, and of course a dashboard solution that can be utilised and monitored by other parties, including facility management and so on and so forth. This is just an idea of what, you've probably seen PLCs and so on from research. But basically these are devices that are able to control different types of signals and also different types of IP and software-driven devices. So basically these devices today can plug into just about anything. The challenge becomes how to operate that software effectively and the stability of these systems in that environment wherever they are, with temperature and all sorts of other issues which can impact on functionality. And that's basically where the challenge lies today. We're using pretty much a state-of-the-art system for most of our controls at the moment, but we do realise that even those devices have limits. And very often the limits come also because of the amount of information that's provided by the manufacturers of different equipment. Sometimes they will not let you into their code, for example, so it gets difficult to control those devices, but increasingly we're seeing some standardisation between manufacturers, which is a very good thing because ultimately, the competitive position of the manufacturer is impacted if they're not able to communicate with other devices. So we're seeing more cooperation in that aspect as well. Just to give you an idea of what some of the things we do as a company, We do have control rooms. We actually have several. We've got one which we're building in Sydney gradually, and it's actually fully functional. We can actually operate devices anywhere in the world, so we can look at the European assets from here, and vice versa. Our team, this is actually a control room in Berlin, and from Berlin they can actually look at our assets in Australia, for example, or in the Czech Republic, or wherever they are implemented, and they can monitor and control them. And the way that works today is basically that they'll do the troubleshooting in the control room. So they might get an alarm. They'll see that a piece of technology is down, possibly an inverter has failed, and or is not functioning completely correctly. And what they'll do is they'll try and find out why that is the case without having to go to site. So these guys generally are troubleshooters to a great extent, and they can intervene from that end. They may change the inverter parameters from a distance, so we're able to do that and see if that helps. They may also trip certain switches and see if that helps, for example, but always with an idea of what they're doing. So basically, at some point, they get to a point where they say, well, it's too dangerous to try anything more, and we'll need to dispatch service to site. So it will be the decision of the operators who sit in the control room as to when they actually send a person out to site to fix something. But the interesting thing is generally they're able to solve most problems, these guys from a remote perspective. So this slide is just basically going back to some of those arguments about where solar storage makes sense. It actually makes sense, as we mentioned, in remote infrastructure. Network investment avoidance is a big thing these days because you have new, let's say, new residential communities, new infrastructure, hospitals, schools or processing plants and so on. And the interesting thing is today you don't need to necessarily be grid connected, or you may be able to utilize a rather small grid connection by integrating storage and generation on site. And you can avoid a lot of cost in this respect. In Queensland, Ergon actually has to do that today. They have mechanisms in place today where they have to look at the alternative to the network investment avoidance. I think they're the first and only still. I think Essential Energy is considering having a similar model, but that's a very important one for the rollout of storage. There's also the demand response, which is an interesting thing because demand response is triggered actually by the AEMO, and the AEMO is very interested in reducing or balancing demands in the energy system to prevent massive price fluctuations, but also to be able to better deploy and adapt peak generation capacities, because they tend to be highly expensive. So peaking gas is a very expensive way of providing short bursts of power necessary to stabilise the grid. So demand response is a very, very important, interesting thing, and storage has an important role to play there because you can actually take part in demand response without actually having to shut down your facility or reduce the power of your facility. So it's a very interesting additional benefit. And of course, load shifting and peak shaving, as we've mentioned, and also improving other aspects of the quality of power. As we know, power factor and active and reactive power are very important from the perspective of energy consumption at the demand source, because at the point of demand, because electrical motors and so on tend to make a real mess of the power and actually make it useless. So you increase your energy demand unnecessarily. Okay, maybe I'd just finalise this just by saying that there are energy solutions out there for energy storage which make sense, which are cost effective, they're flexible, they're reliable, and they're controlled, and they're fully supported, and basically ready to go. So it's more about convincing different players and stakeholders of the benefits and of understanding the costs and also of looking at the value that can be provided from these systems so that it is well understood, and so that people are not afraid to take the plunge into something which we do call the new energy. And that's really sort of the challenge that we have as a company. It's a challenge that I think everybody who's in this room is probably well aware of. It does often come down to how to present information and how to give those convincing arguments, factual arguments that are able to make those types of projects viable. I think that's fundamentally what I wanted to say today. So I thank you, and if you have any questions, yeah, I'm happy to answer those. Yes.
And how long do you think you'll need to replace the batteries?
That's a really good question, because we actually don't know. What we expect is, according to the way we've set up the system, we expect that they will have a 10-year life. So those batteries, the VRLA lead acid batteries that we have in that system, is a 10-year life. Now, the technology itself, if you keep it in a certain state of charge, the shelf life of that technology can be 30 years. So there's a big discrepancy between what we expect today from a conservative analysis and what could happen. So it's still a moving target, but we would expect these batteries to last at least 10 years in that system, and we've accounted for that in the operating costs of that system. So there is some upside. Yeah.
So I don't know if I heard you correctly. You talked about the state of charge in the winter months are quite low, like 50% or something. So do you still charge the entire bank, or you actually charge banks of batteries and let some have a rest?
No, they all work in unison. So we're giving them all the same treatment, and they all go down to lower state of charge. Now, we have considered to run banks in different configurations, and there's quite a bit of research actually being done into combining different technologies. So you'd have a supercapacitor bank, for example. You'd have behind that a high cycling lithium-ion technology, and then you could have another technology which is doing longer term storage, and therefore try and get the cost of the system down while maintaining the output parameters. So there is some research there, but this particular system, very simple in that respect. We never go below 30% of, so the deepest discharge would be a 30% state of charge, and the system is operating with the rest, and that's what is preserving the battery life, basically.
Yes.
G'day. Hey, thanks for your talk. Very interesting. I've had a little bit to do with setting up GPS, continuously operating GPS stations, and sometimes you need to be in autonomous places and running solar and things. And you need 24/7. And I was thinking about what you were saying here, and I'm also kind of struck by the comments from our Prime Minister a while ago about lifestyle choices of Indigenous communities. And a lot of people often think about, what keeps people in Indigenous communities. You also talked a lot about the cost of sending technicians out with jobs. I wonder if you considered if there was some way, and I know this is pretty out there sort of comment, but if there's some way of getting locals who live in the region skilled up to a level where if your remote information isn't enough, you'd be able to communicate with someone in the local community who could actually just do something for you, put them on the payroll, you know. But it's a way of then sort of technology transfer, and I can imagine that these sorts of places, if people were living there, I mean, it'd be a bit ad hoc.
Yeah.
If people were living there, then other places could get.
It's actually, I know exactly where you're coming from, and it's actually done like that already. So basically, what happens is wherever we deploy a system, we always find a local. Usually, it becomes a local electrical company or a local electrician, and that person is basically trained in the particular equipment that is on site and is able to. So We very rarely send a highly trained technician, let's say from Sydney, to go somewhere to fix something. In general, it will be the local person who actually does that. And the challenge can be sometimes to find someone with the basic skills needed. So in general, we do need to have somebody who is a licensed electrician to go in. And we've already looked at sites where there's nobody, where actually some places there is a farmer or a policeman who actually comes and checks something, knows what he can do, and that really does happen. And it's already been happening with companies like BAI, for example. They've been running a lot of their infrastructure in that way, that they have the local policeman or the or a local farmer who's actually trained to come in and do, let's say, the minimum amount of checks and controls on that system to ensure that we don't need to send out somebody. But definitely that's the advantage of these systems long term, that they become part of that community, that they are an autonomous system. It's got strategic advantages. You enable local people to get skills which are important from the perspective of even expanding those systems into the future and bringing employment opportunities to those places and so on. I mean, this whole new energy system has enormous advantages over the existing grid and centralised systems.
The other thing that I thought about too was that in comparison to, say, a diesel generator, there's many moving parts in a diesel generator, whereas one of your systems perhaps less so.
We have hardly any. I mean, really the only moving parts that we have in there would be motorised circuit breakers. The rest is either solid state or chemistry. So it's highly reliable because of the lack of moving parts. So yes, diesel gensets out in mining sites and in other remote locations can be a real problem to keep them up and running. And of course, the biggest issue is getting the fuel to those sites. That costs an absolute fortune. It very often costs more to get the fuel to the site than the fuel cost.
Yeah.
So,
more power to you.
Exactly. Yeah.
Thank you.
I think I saw you first.
Any figures regarding the efficiency of your system?
Yeah, we do have information of that. I think I didn't necessarily put that in there, but the conversion efficiency of the system is about 82.5%.
But how about the battery?
Sorry?
How about the battery? The VRLA?
Oh, you mean efficiency from the actual cycling? Well, that's basically a reflection of that. So what we're saying is that to charge the battery, we've got we actually have, it's quite efficient, that technology today. We're getting over 90% efficiency on the charge, and on the discharge again, so the balance is about that 82.5%. It's not as good as lithium. Lithium technology has a round trip efficiency over 90%. So we're disadvantaged in that perspective, but
yeah, because you charge the battery at very high current, and with discharge battery with low current. Normally, when they have the efficiency curve, over 95%, for example, for the laser iron, they test the battery at particular charging current or discharging current.
It's the C rate.
If you have the flexible one, the efficiency goes down very fast.
Yes.
So that's my question, particular for your system.
Yeah, it's going to be different in different systems because our charge rates and discharge rates are going to be different. So the curve is basically telling us what's happening within the battery chemistry with given current and temperature.
Yeah.
So at that point, when we dimension the system, we'll consider that in the choice of the technology. If we're doing a lot of quick charges and discharges, we won't use lead acid. It becomes increasingly less and less efficient quite fast. But in the sort of situation that we're in, we're getting a round trip efficiency over 80%, which is still quite good. For a battery technology. Our problem would be if we'd be discharging, if the temperature is going up, the discharge and the cycle will probably drop very dramatically.
Yeah. And another thing I'm wondering is that do you use the battery to discharge one by one, not all of that, because that will solve this problem. You set all this at the optimal current.
It's running. It's basically that system has 3 strings. And each of them are working in parallel. I mean, from a perspective of charging discharge rates, so they all work at the same level. in that system. No problem.
Yeah, you actually sort of provided an answer to my question. My question relates to the curve you showed with a sweet spot.
Oh yeah.
And my question really is, I presume as the system gets bigger and bigger, you have the ability to cluster network element and have, from a redundancy perspective, things work in parallel rather than in series. So I would presume that curve perhaps would have a sensitivity to the overall size or magnitude of the system, and by clustering network elements appropriately from a redundancy perspective, you would be able to extend the mean time between critical failures and maybe also reduce the time to repair. Is that something you consider?
Yes, absolutely. Basically the sort of redundancy we have in that system is that we can run it with, they can run in, each string can run independently. So if you have a failure in one string, we can turn that off. So there is that ability. So there is that possibility that if something does go wrong, you can run the system in a sort of a reduced regime. If the weather's going to be good, it's not going to make much difference. If the weather's going to be worse, it means your diesel genset's going to have to run more. Absolutely.
As we get bigger, do you think you can reduce cost and enhance overall reliability?
Absolutely, yes. Because generally how those, the bigger systems are working, and we're working on quite a large lithium-ion system at the moment. Now, what's happening there is that we've got blocks of batteries, and each of them will function independently. So if one burns or has a failure, we don't want it to ever burn. It has got a fire safety system internally. But if something happens, the system will continue to operate. So that level of redundancy, absolutely has to be built in. In fact, the customer spec always has a redundancy element. So if we don't meet that redundancy element, we would it would be quite problematic. But I think what you're alluding to is right, and these are areas that need to be investigated further. If we look at battery systems, especially large battery systems, very often there are situations that occur, open circuit, short circuit system within battery string, and that can cause a battery string to fail. So, in the ideal world, you could have a bypass, an automatic bypass, to preserve the string.
If you look for knowledge in that area, the space industry has done a lot of work in that area, in redundancy and redundancy principles and methodologies, etc. So that might be an area if you need to find.
Thank you for that. Thank you. We've noticed with the lithium-ion technology that very often that's already starting to be built in, the bypass technology. So that's one aspect where it is. With lead acid, it's quite difficult. It's quite a challenge because you don't have a BMS on each battery. But then again, within a lithium-ion system, you're generally talking about a cluster of cells controlled by one BMS. So there's you don't necessarily, the BMS will not necessarily react to one cell failure within one battery, but certainly between batteries, yes.
Mike, thank you for your presentation and congratulations on building a successful new energy business.
Thank you.
I'd like a question from the investment banking side of things. Given your experience in both areas, we need the investment community to support such projects in order for new energy to continue growing. From your perspective, are the investment community people convinced about the profitability of PV in today's market, and also what are the risks that we need to get them over in order for this to really take off? Yeah. Fundamentally, financing renewable energy projects is about it's about two things. One of them is looking at the support mechanisms that are available that reduce the risks for the investor. So the feed-in tariff mechanism was actually beautiful from that perspective because it gave them a 20-year guarantee of income on a certain system. So you only have to really worry about the technical side, make sure your system produces enough to be able to cover all your financial return. Now, in a world without feed-in tariffs,
it's all about credit risk. So you'd be looking at different aspects. For example, if it's a commercial entity who is investing in a solar and a power storage system, it would be the bank coming in and looking at them from a credit perspective and saying, well, look, it's pretty much the same as if they wanted to buy any other asset. So it would, if they buy a machine or the PV system and so on. And the bankers are quite responsive to that today. They actually have got product finance available that is looking directly at renewables and power storage increasingly. They're still very edgy about power storage, to tell you the truth. But at least in the PV space, they've become quite open to financing corporate credit risk with PV, and really looking at it from an equipment finance perspective, same as leasing and so on. But from a grid perspective, which is a completely different aspect, I still think that that there will be a role for the regulator to play here, because the most important thing is how you actually are able to price the service provided by PV and power storage from a grid perspective. And the problem is that the system has not been set up and regulated in a way that's attractive for embedding those technologies into the grid without a feed-in tariff mechanism or some other mechanism. But I think there's a lot we can do to improve the investor, let's say, support for those projects by actually changing the way we regulate the power system from a grid perspective. Mm-hmm.
More questions?
A quick one. Have you done domestic storage systems? And if so, if it was lithium-ion, where did you put the battery bank?
Now, we haven't done residential. We don't really dabble that much in residential, but we do have a small power storage system which we use in our office. So we've got it on the balcony of the office building, and it was quite interesting to get permission to do that, because we had to ensure that we're not going to burn the building down and so on and so forth. But we've used lead acid technology in that one, so not lithium. So it hasn't been such a big problem. But actually, a big question was raised because we wanted to have some lithium batteries there, and they actually prevented us from using them. They said, sorry, it's too much of a risk.
Who's they?
It was the building owner.
Because there's no rules and regulations?
Because there's no rules and regulations. It's because we've positioned it on the balcony of the building. They were quite concerned that if a fire did occur that we could burn the building. I mean, I don't want to paint a bad picture about lithium-ion, certainly not, because it's a very good technology and the risk of fire is extremely low, actually, today, by the way that the cells have been manufactured. But even in that sense, everyone's looking for guidance. They're looking for regulation that says this is how you can deploy a lithium-ion battery in a residential perspective or in an office building. Yeah.
So let's thank Mike again for the talk.
Thank you very much.